Hi there, this is Deanna. For our project, we've been tasked with picking one of 10 projects and making a video that shows what we've learned. I've looked over our 10 projects and I couldn't decide, so I'm just going to do all of them. First, I'm going to prove the Pythagorean theorem. Then I'm going to figure out Mark Wilson's card trick.
Then I'll demonstrate the card sorting system, and I'll build 5 platonic solids. Then I'm going to create all the possible tessellations using regular polygons. Then I'll build a tetrahedron and the cube it fits in. And I'll answer what regular or semi-regular 3D solids tessellate 3D space. Then I'll build them, and I'll show how they tessellate, and I'll show how we know there are no others. Then I'll tell you which polygons make pyramids whose sides are equilateral triangles that have different bases. I'll build them, and I'll explain them. Then I'm going to build star-shaped polyhedrons discovered by Kepler and explain the process. And construct Mobius strips, and then cut them parallel to the edge according to the text and demonstrate the process and explain the results.
Then we're going to pass through the 7 levels of the mosaic forest, through the sea of swirly twirly sequences, and then we're going to walk through Euler's path. Well, that would be fun, but in the eternal words of Sweet Brown,
ain't nobody got time for that. Ain't nobody got time for that. Ain't nobody got time. Ain't nobody got time. Ain't nobody got time for that.
So, the project I've chosen to do is I'm going to build the 5 platonic solids and answer the question, how do you know there are no others? So, let's get started. First, let's talk platonic solids for a minute, shall we? The reason they're called platonic has nothing to do with their relationship status, but everything to do with Plato, the person who gave instructions for making models of them in the 6th century BC. Plato had some ideas about the shape of the atoms and how they related to the shape of regular polyhedra. The universe was supposed to be in the shape of a dodecahedron, Earth, cubes, air, octahedrons, fire, tetrahedrons, and water, icosahedrons. Sounds a bit out there now, but the polyhedron models have been a great value to the science community ever since. So, what is a platonic solid exactly? In 3D space, a platonic solid is a regular convex polyhedron. Regular meaning that all the edges are the same length. Convex meaning they poke out and they don't indent. Each platonic solid is constructed with identical regular polygonal faces, and each polygon has equal edges. And each corner of the solid has the same number of vertices. So, only 5 solids meet those criteria. Why is that? At each vertex, at least 3 faces meet, and it could be more. And when we add up the internal angles that meet at a vertex, it must be less than 360 degrees, because if it was 360 degrees, the shape would be flat. And the platonic solids are convex, don't forget. So let's test it. A regular triangle has internal angles of 60 degrees. So if we have 3 triangles times 60 degrees, that's 180 degrees. And that works because it's less than 360 degrees. And so that actually is a tetrahedron. 4 triangles times 60 degrees, that's 240 degrees. And that works because it's less than 360 degrees. And that's actually an octahedron. 5 triangles, that would be 300 degrees, again less than 360, and that's the icosahedron. But if you had 6 triangles times 60 degrees, that would be 360 degrees, and that is a nobahedron. A square has an internal angle of 90 degrees, so it has 4 corners, and inside each corner it's 90 degrees. If you have 3 of those coming together, you would have 3 times 90, and that's 270 degrees, and that's less than 360 degrees. So that's our cube. But if you tried to do it with 4 squares, and 4 times 90 equals 360, so that won't work. It would be flat, and that's a nopahedron. A regular pentagon has the internal angle of 108 degrees. So if you take 3 pentagons and use those, that would be 3 times 108, and that's 324 degrees. And that's less than 360, and that's how we get our dodecahedron. 4 pentagons, that would be 4 times 108 degrees, and that equals 423 degrees, which is more than 360 degrees, and that's a nopahedron. A regular hexagon has internal angle of 120, but 3 hexagons would equal 360 degrees, and that's another nopahedron. So as you can see, we've ended up with 5 instances where it works and it stops at the pentagon. Plus, there's another proof of concept at work here, and that is Euler's formula. F plus C equals E plus 2. Faces plus corners equals edges plus 2, right? And that only works for these 5 solids: tetrahedron, cube, octahedron, dodecahedron, and icosahedron. Okay, now let's build. First, let's grab some supplies. I found these used file folders hanging around. I was going to use OakTag, but I tracked down my 5th grade teacher. She told me they stopped making OakTag when I was in 5th grade. The other things you'll need are some tracing paper, some tape, a pencil, a ruler, some scissors, and something pointy or sharp to poke holes. I'm using this compass, and also something to score your paper with. I'm using this object here. It makes it easier to fold. You'll see. First, I'm going to place the tracing paper over the pattern in the book. Then I'm going to make a dot on each vertex. Then I'm going to connect each vertex using the ruler. You're going to want to do that for all the different shapes and using your tracing paper to do that. Next, place the tracing paper on top of your file folders. I use a stack of them so that the point doesn't harm the table. So go ahead and poke a hole in each vertex. When you pull the tracing paper away, you'll see the holes that are left there. You're just going to want to connect those using your ruler and your pencil. Again, you're going to want to do that for all the different shapes and the patterns in the book. I'm working with the tetrahedron. The other patterns, you have to cut out 2 of each. So you would do that twice. So here is my cutout shape for the tetrahedron, and you're only going to cut out the outside edge, not the lines on the inside. For the lines on the inside, I'm just going to use my tool here and make a mark, and it's going to make it easier for me to fold it later on. Then you fold up the edges and tape the edges together. And there's your tetrahedron. And to make all of them, you would just go ahead and continue the process to complete your cube, your octahedron, your dodecahedron, and the icosahedron. And before you know it, you too can have a bowl of platonic solids.